This is Lindsay Clark, your primary instructor for current topics in medical laboratory sciences, and we are on lecture 28. This is the second part of quality control and laboratory statistics. In this lecture, we are going to focus a little bit more on the statistics used in the lab and how those relate to your quality control. Your objectives for today's lecture. Number 1, define and differentiate sensitivity and specificity and calculate both with the appropriate data. Number 2, list criteria needed to establish a reference range, including the number of individuals that should be tested and factors to be considered. Number 3, define the following terms and discuss their pertinence to laboratory statistics: accuracy, precision, mean, median, mode, standard deviation, and coefficient of variation. Number 4, when given appropriate data, determine the mean, median, mode, standard deviation, coefficient of variation, and confidence limits. Number 5, state the expected percentage of values that will fall within 1 standard deviation, 2 standard deviations, and 3 standard deviations. So here's a quick overview of today's lecture. We are going to start by defining sensitivity and specificity, and we'll discuss diagnostic versus analytical sensitivity and specificity. Then we'll define accuracy and precision. From there, we're going to talk about reference ranges, what they represent, and how they are determined. We'll review the mean, median, and mode, and then we'll go over standard deviation and coefficient of variation. Sensitivity and specificity, along with accuracy and precision, are test characteristics that are important to QC and quality assurance. They can help determine which test methodology is best for your lab. So they're included in this lecture for their pertinence to quality control. Starting with sensitivity and specificity, when we talk about these, we need to distinguish between diagnostic and analytical. Diagnostic sensitivity and specificity refers to the ability of tests to detect a disease when it is present or not detect a disease when it is absent. Analytical refers to the test methodology's ability to detect small amounts of an analyte and to detect only that analyte. So this chart is a good overview of your diagnostic sensitivity and specificity. Diagnostic sensitivity is the proportion of individuals with a disease who test positive. So a 100% sensitivity means the test is able to correctly identify every person who has the target disease. Diagnostic specificity is the proportion of individuals without the disease who test negative. A 100% specificity means the test is able to correctly identify every person who does not have the target disease. The formulas for calculating diagnostic sensitivity and specificity are similar, so make sure you are using the correct formula when you're working these problems. Now, to calculate diagnostic sensitivity, you will divide the number of true positives by the true positives plus false negatives, and then multiply by 100. And this gives you a percent sensitivity. For specificity, you divide the true negatives by the true negatives plus the false positives, multiply by 100, and this gives you a percent specificity. Now, in general, you want your sensitivity and specificity percentages to be high. You want them to be close to 100%. So a lot of times you'll hear tests in the lab that have a 96% sensitivity or 98% specificity, and this is what that is referring to. So a quick example of how to calculate specificity. So let's say we have 1,000 individuals tested. We have 600 of them that we know have the condition that we are testing for. So those 600 are known positives. Now we want to compare our current test method to a new method. Our current method detected 625 positives. 25 of those were false positives. Remember, we have 600 that we know are truly positive. So the 25 there are false positives. And this method also detected 375 negatives. 50 of those were false negatives. Now, using this data, we can calculate the specificity of our current method. So we take 325 divided by 325 plus 25, multiply times 100, and we get 92.8%. This is a pretty good specificity, meaning our current method is pretty good at detecting true negatives. The new method, however, detected 875 positives. 275 of those were false positives. It detected 125 negatives, and 25 of those were false negatives. And now if we calculate the specificity, we get 26.7% for the new method. This is a very low specificity, and this indicates this method is not very good at detecting true negatives. So based on this data, we would certainly want to stick with our current test method that has a higher specificity. And if you were to calculate sensitivity, it would be very similar to this. Analytical sensitivity and specificity are different than diagnostic in that they refer more to the test methodology. Analytical sensitivity is the smallest concentration of a given analyte that can be accurately measured above zero. This is sometimes called the limit of detection, or LOD. Now we want to know that our test method can detect very small amounts of the analyte, and so this is important to know the analytical sensitivity. Just as important is the analytical specificity, and that is a method's ability to measure only the analyte of interest. So we want to know that our test is specific for that analyte so that we're confident when we report out results that it's actually reporting the results for that analyte. Accuracy and precision are also really important test characteristics. Accuracy is defined as the closeness of the result to the true value. Precision is the reproducibility of a test. So you want your method to be both accurate and precise, meaning you want to get the true value every time. Okay, let's move on to reference ranges. Reference ranges are defined as a range of most likely values for a healthy population for any given analyte. Now, to determine this range, a series of healthy individuals are tested and the results are averaged. Then we will determine the standard deviation, and we use this plus the mean to determine the range. And this range reflects a certain level of variation. And the reference range should estimate the middle 95% of values produced by that population. And remember, we're talking about a healthy population here. So remember this 95%, it's going to come into play here in just a minute. To establish your reference ranges, you want to use no less than 20 individuals. Testing more individuals is actually better. It provides a better estimate of the population, and it will result in less variability. When choosing these individuals to be tested as representatives of your healthy population, you want to consider things like age, sex, genetic factors. You want to make sure you have a set criteria for inclusion or exclusion of individuals. Consider the time and date of collection. Think about intake of food or drugs and so on. Make sure your specimens are properly collected, and you want to consider the analytical method being used. Now the images here are some examples of reference ranges. You guys are all familiar with reference ranges. And triglycerides is a good example of why you would want to consider food intake before your specimen collection. Say we test 100 individuals, but 36 of them ate cheeseburgers before the blood draw. That is really going to skew your results, and then that reference range is not going to be quite right. And the same thing with glucose. So you want to make sure your individuals being tested are actually fasting if you're drawing a fasting glucose. If they're not, again, that's going to skew your results, and then your reference range is going to be off. Let's move into the statistics now. I'm sure you are all familiar with mean, median, and mode, but let's run through some quick examples just as a refresher. The mean is the mathematical average. So let's say you have these numbers. We have 3, 6, 5, 9, 12, and 7. Now to get the mean, you want to add these numbers together. When you add these numbers together, you get 42. And then we want to divide by 6 because that's the number of numbers that we have. And this is going to give us 7. So our mean for this set of numbers is 7. And the median is the middle point. If you have this set of values, you first need to put them in order, and you can put them in ascending or descending order. It doesn't really matter. So you put them in order, and then you find the middle number. So in this case, your middle number is 5. Now, if you have an odd number of values, you would take the middle two numbers and average them to find the median. And finally, the mode is the most frequently occurring number in a series. For this, I like to put my numbers in order just like I would for the median. So I'll put them in order. And this allows us to see more easily that our mode for this set of numbers is 3, because we have 4 3s there. So that's the most frequently occurring in that series. Standard deviation. So standard deviation is a statistical description of the distribution of all values around the mean. So it's a measure of variance, and it is used along with the mean to determine those acceptable reference ranges. Now, when you look at this formula, it looks pretty scary, but we are going to break this down and work it through step by step. So don't get overwhelmed by looking at this equation. We're going to work through it. The formula for standard deviation is this. So you have S equals the square root of the sum of a data point minus the mean squared over n minus 1. So in this equation, your x bar, which is the x with the little bar over it, represents the mean. Your n represents the total number of data points, and your x sub I represents one data point. And so you can substitute for that I in the x sub I. You could substitute x sub 1. That would be your first data point. Or x sub 2, which would be your second data point, and so on. So we can break this formula down into the steps, and those are listed here. So the steps to calculate standard deviation. First, you're going to calculate the mean. We know how to do that. It's pretty simple. Then we're going to subtract that from each value. We're going to square the difference, add the squares. Then we're going to subtract 1 from n, and we will divide the sum of the squares by that n minus 1 number. Then we take the square root of that number, and that will give us our standard deviation. So we are going to work through a practice problem next, and I've posted this problem in Blackboard as a printable document. So if you'd like to print it out and kind of follow along and make some notes, that document is available for you in Blackboard. So here we go. Let's say we have these 10 values, and we want to calculate the standard deviation. So our 10 values are listed here. The n, again, represents your data points, and the x sub I is your value. Step 1, we will calculate the mean. To do this, all we have to do is add all the values in the right-hand column. We add these up, we get 100. Then we just divide by the number of values. So how many values are there? There are 10. So simply 100 divided by 10, and that equals 10. So this is our mean, or our mathematical average. So we want to make sure that we remember what our mean is, because we will use this throughout the rest of our practice problem. Next, we want to subtract the mean from each value. We have our original values in the first column. In the second column, we subtract the mean from each value, and our result is in the third column. So for row 1, our original result is 10. We subtract the mean, which is 10, from the value, again 10, and we will get 0. And for the second row, we would subtract 10 from 6 to get -4, and so on. So you'll go through all of these and subtract the mean from the value. Now for a quick check, if you want to check your work so far, once you have all those numbers, if you add up the third column, you should get 0, or you should get a very small number that is close to 0. If at this point you add those up and you get a large number, you want to go back and check your work. So this number should be very close to 0. So now we have our x sub I minus x bar values. So that part of the equation we have figured out. Now the next step is to square this number. So in the fourth column here, we square those numbers. In the first row where we got 0, we square that and you just get 0. The second row, we had -4. -4 squared is 16, and so on. So you want to square all of those. Next, we want to sum the squares. So we just want to add up all those numbers. So we're going to add up all those numbers, and that gives us 60. So now we have calculated a large part of our equation. So the sum of the value minus the mean squared. So this part of the equation we have calculated and we know to be 60. So remember here at the top, let's remind ourselves what our whole equation looks like. And again, we have calculated this part of our equation already, and we know this to be 60. So we can plug that in there in the equation. So this does not look as scary anymore, right? So let's move on. We are now going to subtract 1 from n. So n, remember, is equal to the number of values we have. So how many values do we have? We have 10. So n minus 1 is just going to be 10 minus 1, or 9. So now we will divide the sum of squares by n minus 1. Now we know the sum of square is 60, and the n minus 1 is 9. So 60 divided by 9, and that's going to give us 6.67. And the last step is to take the square root of this number, and that's going to give us our final answer. So our final answer is 2.58. This is our standard deviation. So we need to talk about Gaussian distributions for just a minute. This is sometimes pronounced Gaussian, Gaussian, depends on if you're French or German, really. So these distributions, they're also called normal distributions or bell curve. And if we were to chart our values in this process and determine the curve, it should give us a normal bell curve for a healthy population, just like we see here. So in any normal population, 68% of the data will fall within one standard deviation. 95% of your data will fall within 2 standard deviations, and 99.7% will be within 3 standard deviations. So what does that look like on this curve? So we have one section between the mean, which is the center line, and 1 standard deviation. So that is going to be 34%. And that is half of 68%. So the other half, we have sort of our -1 standard deviation. That's also going to be 34%. So that gives this whole area, which is a plus or minus 1 standard deviation, makes 68%. Now from one standard deviation to the next area, the second standard deviation, this area is actually 13.5%. And it's the same for the other side, 13.5%. So if you add the area, we have this area that is 68%, and we add our two new sections, 13.5% plus 13.5%, that gives us this whole area, which results in 95%. And then our little 3SD areas around the side there, those are going to be about 2.35% each. And again, you've got 99.7% of your data will be within those three standard deviations. And so that's just kind of a visual there of how that data plays out. So let's look at this using the data that we calculated for our example problem. So we know our mean is 10. So the center line here represents 10, our mean. And our standard deviation is 2.58. So first of all, let's talk about how we determine two standard deviation and three standard deviations. It's very simple. You just multiply. So two standard deviations is 2.58, or one standard deviation times 2. And that gives us 5.16. Now, three standard deviations is just 3 times 2.58, and that gives us 7.74. Now on the curve, each section that is one standard deviation is going to be 2.58. So we have 2.58 in this section, and that's from the mean to plus 1 SD. And really, you can think of it as a minus 2.58 from the mean to your minus 1 SD. And then we have 2.58 in this section, minus 2.58 in this section, 2.58 in this section, and so on. So if you look at this curve and you wanted to calculate 2SD, you could add each standard deviation section. So you could add this section to this section, and this is going to give you your plus 2SD. 2.58 plus 2.58 is your 5.16. My beautiful drawing here with my mouse. So you could do this if you wanted to do it this way and look at it sort of visually and decide. So what is our reference range for this data? So that's ultimately kind of where we're going with all of this. So to determine your reference range, we will take the mean plus or minus 2 standard deviations. So right now we have a plus 2 standard deviations, so then we could take this section and that would be our minus 2 standard deviations. And remember, this whole section here is 95%, represents that middle 95% of your healthy population. Okay? And that's why we're going to use our 2 standard deviations versus your 1 or your 3. So if we take our mean, which is 10, and we subtract 5.16 to get the lower end of the range, we get 4.84. Then we'll take our mean and we will add 5.16 to get the upper end, which is 15.16. So our reference range for this data is going to be 4.84 to 15.16. And that represents, this here would be your 4.84, and this would be your 15.16, and there is your range. So lastly, we want to calculate our coefficient of variation. CV is a measure of precision. It tells us how much variability there is. It is unitless, and because it sort of normalizes or standardizes values, it's often used to compare different sets of data that may have different means, or maybe they were measured using different scales. CV, in terms of the lab, might be used to compare standard deviations of test results that are expressed in different units or different concentrations. Or it might be used to compare test results from 2 different labs. So a visual representation here, if you have your mean, which is the straight line on the chart there, the CV is measuring the variation in the points around the mean. So you generally want your points to be closer to that line, so there is less variability. Less than 5% is generally a good CV, but there are always exceptions to that. So let's calculate our coefficient of variation using the data from our practice problem. So our formula for this, CV in percentage, is the standard deviation divided by the mean times 100. Our standard deviation is 2.58 and our mean is 10. So we will divide 2.58 by 10, multiply by 100, and we will get 25.8%. Now this is a fairly high CV, meaning there's a good bit of variability in the initial values that we started with. So those were kind of just random values that were chosen for this practice problem, and so there's a good deal of variability. That is all we have for today. So there are 2 more practice problems posted in Blackboard for you to work through. It's one printable document, and these are sort of example QC values. So if you were running a normal sodium QC and running a high sodium QC for 10 days, you mark down all of your values, and then you're going to walk through the steps just like we did in the lecture. So you'll calculate the standard deviation, you'll calculate the mean, you'll calculate your coefficient of variation, your reference range, everything that we just went through in the lecture. So you need to know how to calculate these values, and you need to know how to do it with a simple non-programmable calculator. You will not be able to use a programmable calculator when you take your boards. So you want to work through these problems with a simple calculator to get used to it, and if you have a programmable calculator that can do this for you, you can always check your work with that calculator, or there are lots of standard deviation calculators online that you can use to check your work. If you have any questions while you're going through all of this, please reach out to me, let me know, and we can chat through email or through Skype or Zoom or however you would like to meet, and we will walk through some of these problems. And here are your references for today's lecture.